Yeah, so you spent the last episode discussing what an array language is. And I'm an academic, so I'm a big fan of discussing definitions. And to me, array language is a social definition. So my definition would be that it's an array language if you get to talk about it on Arraycast.
Well, he's got us there.
Welcome to another episode of Arraycast. I'm your host, Connor, and today with us we have a special guest who we will get to introducing in a second. But before that, we're going to go around and do brief introductions. We'll start with Bob, then go to Rich, then go to Marshall, and then go to Stephen.
I'm Bob Therriault, and I am a J enthusiast working on the wiki, and that certainly keeps me busy.
I'm Rich Park. I'm an APL programmer and educator working for Dialogue Limited.
I'm Marshall Lockbaum, former J programmer, former Dialogue developer, and a current BQN designer.
And I'm Stephen Taylor, APL and Q programmer.
And I think we have 1.5 announcements. So we have half an announcement from Bob and then 2 half announcements from me. So we'll go to Bob first.
Okay, my half an announcement is that I always say that I'm a J enthusiast, singular. I'm not sure what the referred to is as a group, but collective, I suppose. I'm one of many. I spent this weekend with a lot of the J software people, had a wonderful time down in Victoria, and I may be moving towards being the J enthusiast. So not saying that there won't be others. Marshall suggested that maybe that was my job to go out and eliminate other J enthusiasts. That is not what I mean. I mean, like, I may be a person who primarily promotes J, and many people will call that evangelist, but I'm anything but an evangelist. I do not push things on people, but I'm very enthusiastic. So that is my announcement that full disclosure, if I start to sound like I'm really enthused about J, hopefully I've sounded that way already. But if I do sound more enthused about J, realize that I may be the J enthusiast.
All right, so we will have to monitor Bob's enthusiasm levels and get some, what do they call that, metrics or whatever over time?
If we do more YouTube, we may have a sort of a meter on the side that indicates how enthusiastic I am.
All right, listeners, keep track and let us know if Bob gets too out of control. My 2 half announcements. The first half announcement is that on my other podcast, ADSP, the most recent episode was entitled The K Programming Language, where Bryce, my co-host, asked a bunch of questions about the K programming language. I can't verify that everything I said was true, but if you're interested in the content that gets talked about on this podcast, you'll probably be interested in that episode. And the second half announcement that I just remembered while doing this whole intro was that I gave a talk when this comes out, it will be a week ago, so just sort of mid-September. That was at the Paradigm Conference, sort of the isolangconf.com that we have mentioned before, where it was a hackathon for high school students and also, I think, first-year university students if they had only taken, one computer science course. And that talk was entitled Popular versus Less Well-Known Programming Languages, and sort of compares and contrasts 5 popular languages versus 5 less well-known languages, which is what the hackathon sort of was endorsing to use for your projects. And one of those is APL. So if you're interested, once again, in the stuff we talk about here, you might be interested in that talk as well. So with all of that, you can find, show notes, all the links will be there. And with all that out of the way, I'm excited to introduce today's guest, Troels Henriksen. You will have maybe not heard his name before, but at the tail end of our last episode, we started talking about Futhark, which is a language that he works on. So a little bit about Troels. On his website, you can find him at sigkill.dk and also sigkill_DK on Twitter. It says that he's a Danish hacker and a general enthusiast in all matters computing. He's presently an assistant professor at DIKU. I'm not sure if they pronounce that differently, which is the computing department at the University of Copenhagen. And as mentioned before, works on optimizing compilers for data parallel languages and is currently working on the Futhark language, which is, I think, what we are going to mainly focus on today. But I'll throw it over to Troels. Feel free to take us back to whatever year you want to. Tell us the story of, how you got into computing and how you ended up working on this Futhark language.
All right. Well, I can take it all the way back to when I started. Well, so my history is actually pretty conventional. I like playing video games, and I had this vague idea that I wanted to do something with computers. And then I remember it was one summer in the summer between elementary school and high school in Denmark, which is when you're about 14 years old, I found one of my dad's old books about DOS. And it was partially basic stuff like this is what the file system looks like and so on. But it actually went quite far and ended with assembly programming in 16-bit real mode on x86. And I didn't have access to a DOS machine at that point, but I really liked the descriptions they had. Especially I liked the descriptions of the command line, the idea that you could have a textual conversation with a computer. I was used to graphical user interfaces, and this idea that you could talk to a computer in text really, really gripped me. So I knew that DOS was obsolete, but I heard about this Linux or Unix thing where that still used command lines. So pretty much from one day to the other, I installed Linux and tried to learn how to use a command line, and I've been doing that ever since. And then I took the usual path of studying computer science at university and learning more and more about programming in my own time at school. And it just grew from there, and I'm still around university, I guess. I mean, academics are just students who never figure out how to leave.
And so that was at 14, you said, that you picked up that book and then ended up installing Linux at age 14? That's pretty impressive. Can't say that I was even successful the first time I tried to do that when I was in university.
I wasn't successful. I installed Debian, and Debian didn't have the right driver for my graphics card. So the first thing I had to learn was how to use VI to edit the X3 configuration file to ask to use a different driver. I have no idea why I put up with it or why I didn't give up. And today I would have given up.
Yeah, well, I guess at the time they didn't have like PowerShell, which is kind of similar to CLI stuff for Windows, but I guess Mac did at the time. Has Mac always had?
Yeah, they've always had CMD, right? But that's
yeah, but I didn't have a Mac.
I love hearing the command line described as an advance on the graphical user interface.
Yeah,
it's like still an improvement on its successors.
No, I see things like that. There's a company called Textualize that's like the Python rich text thing. The guy who does that is working on an entire framework for building text-based user interfaces. I think people have gotten to the point they're like, man, this GUI stuff doesn't work, does it? No one's figured out how to make a good-looking GUI. Let's just go back.
We'll put links in the description to the Textualize thing. I mean, it is pretty impressive. There's a bunch of stuff. I mean, if even the J interpreter, when you run it, is very impressive, the stuff that they're able to render in terms of the boxing and whatnot. But anyway, so you end up going, did you study at University of Copenhagen? That's where you did your undergrad and your
Yes, yeah, I did my undergrad at University of Copenhagen. And we were taught functional programming, standard ML as the first language.
Really?
It was pretty cool. So I picked up Common Lisp a few years earlier. So I was dimly aware of the idea of functional programming, which you can do in Common Lisp, even if it's not always idiomatic. And but what was new to me was static type systems as in standard. I mean, I've done a bit of C and so on, but those are pretty simple. So that was quite eye-opening. And a few years later, I learned Haskell, and then that's probably been my primary language ever since. I got into array languages kind of by accident or by coincidence. So I made my way through university by being a teaching assistant. DIKU has a pretty strong tradition of hiring undergrads and early graduate students to help tutor other students. It works pretty well. And I've been a teaching assistant in a compiler's course under a newly hired postdoc, Cosmin Oancea, who will eventually go on to be the co-creator of Futhark and actually the originator of it. This course was built around having the students, they were given a draft of a compiler, and then they had to finish it. So improve or extend the parser, the type checker, code generator, all that's pretty standard stuff. But I didn't really like the way that Cosmin had designed the compiler. There were some technical things. It was written in standard ML, and I think I felt that some of the things were not done as well as they could be. So after the course was done, he sent an email to the TAs saying that he was starting up a new research effort to construct a compiler for a parallel language. And I didn't really care that much about parallelism at the time, but I cared a lot about compiler design. So I joined just to show off how I thought that a compiler should be designed. And the first thing I did was rewrite it from standard ML to Haskell. I think they only put up with me because I actually wrote some code that worked. I don't think Cosmin really cared which language it was in. He just cared that someone was doing some work. And that compiler, initially it essentially compiled a very tiny subset of standard ML to sequential C code or passed it to an interpreter or whatnot. But eventually that compiler grew to be Futhark.
Interesting. So maybe before we hop into the technical details of Futhark, for those listeners out there that only maybe heard about Futhark for the last episode, what's the maybe overview of Futhark, the language, for those that haven't heard anything about it?
So Futhark is a language in the ML family. So it looks a little bit like Haskell or Standard ML or Ocaml, and it feels like programming in Standard ML or Haskell or Ocaml. And the kind of win or the benefit of Futhark is that it can be compiled to parallel code. That's pretty much all it's for. So it has lots of limitations. It's not nearly as nice as standard functional languages, but it runs pretty fast. That's the
so basically a functional ML language that can be accelerated. And is it just onto GPUs, or is it any sort of devices that do parallel computation?
It's a hardware agnostic language. It doesn't expose any low-level details. Our best compiler generates GPU code, but we also have a compiler that generates multi-core CPU code, and even one that generates code for ISPC, which is Intel's vector CPU language.
Okay.
So heavily vectorized CPU code.
And what is kind of the state of the language? Is it still kind of a research level language, or are there companies or teams out there that are actually using this to run sort of parallel computations?
I mean, it is definitely a research language, and it's a very obscure language. But it's documented and it's stable, and there are people who are using it for some form of production. I think most users are themselves academics who need to write simulations or models or whatnot that are more flexible and can be expressed by just putting together Numpy or PyTorch or TensorFlow primitives, but that need to run faster than they would if they just wrote them in Haskell. So there's this kind of very small niche. I'm not sure how big it is, whether it even really exists. And the few Futhark users there are tend to be in that niche. I also sometimes hear of companies that use it, but I think it's mostly for internal prototypes and experiments. It's a very obscure language. I mean, what we're researching is compile optimizations. It's great if we can create a useful tool, but that's more of a hobby thing. The language design is my hobby, and the research is what's supposed to be my job.
And this is and I'm sort of hogging all the questions, so I'll let. I'm sure Marshall has 1,000 questions that he wants to ask as well. But the last question I'll ask is, because you're probably a great person to ask this, is you said it's a very small niche that is being programmed for. But I'm aware of single assignment C, and you even shot me a note about that. Are there other languages or is it just single assignment C and Futhark, or are there other languages or libraries that sort of operate in the same space adjacent to Futhark?
No, there's a bunch of them. So you could even argue that Codfns, that is the APL compiler that targets GPU, is in the same niche. Mm-hmm. And there's also DEX, which is done by Adam Paske and Dougal McLaurin at Google, mm-hmm. which is fairly recent. And there's a handful of these. There's Accelerate for Haskell, which is a Haskell embedded language. Mm-hmm. So there's a bunch of these, and they are all pretty niche, but they do pop up here and there. There was Copperhead for Python once, but I'm not sure. I don't know of any that are really penetrated into wide use. The closest you can get are probably these the GPU DSLs in Python, like TensorFlow and JAX and so on. They're the most similar things.
Interesting, yeah. So we will put links to all of those for folks that are interested, because it's definitely basically like very adjacent to what I do for work. But yeah, all of those projects that were enumerated there by Troels, we'll throw links in the show notes for us. All right, I said that was my last question. I'll throw it to Marshall or whoever's got the next thing that they want to ask about Futhark or anything. Go ahead.
I don't know if I'm a great question asker, because I have read a fair bit about Futhark, but one thing that struck me as I read was that you have a lot of work done by students and often kind of short-term projects. So I was kind of interested about how that works, how it is getting, a lot of new developers adjusted to the project and getting them to make a contribution in usually a year or so.
Yes, so that's interesting. The original motivation for doing that was that when I was a student, I was really starved for interesting projects. And I had infinite free time, as students tend to do, and I just wanted something cool to do. So when I became a PhD student and later on a professor, I just wanted to make sure that the students didn't go through the same thing, that they actually had something interesting to work on. So I tried to come up with interesting projects for them. Eventually, later, I've grown jaded, and I'm just seeing them as a source of free labor, of course. and originally, we didn't really plan on the best way to integrate students, and it was kind of random whether the projects worked out or not. Later on, we've become more conscious about this, about coming up with projects where the students only have to study or work on a small part of the compiler, because it's a big compiler now. It's a big optimizing compiler for a non-trivial language. It's written in Haskell, which not all of the students may be familiar with. So our most successful projects tend to be the ones that focus very narrowly on either front-end stuff or tooling, or very back-end stuff. Because when you're working in those areas, you only have one interface. You're only concerned either with what you receive from the rest of the compiler, or what you have to pass to the rest of the compiler. Whereas when you're working in the middle of the compiler, you kind of have two different customers or two different interfaces, both what comes in and what comes out, and you can't change either of those.
So what kind of stuff does go in the middle? Is that
optimization passes?
Yeah, so you have some sort of intermediate representation, and you're working with that.
Yes, and those are tricky, especially the use of the optimization passes that transform the representation. I mean, the ones that are kind of working on the same representation, those are not so bad. But when you have to do work, change from one representation to another, or even extend the representation, those are beyond most students, unless they are exceptionally talented or have lots of free time.
Yeah.
And something you said, source of free labor, and actually, if anybody's going into academia as part of what may become a source of free labor, just understand that is the case, because as I went back for my master's degree, it became apparent that students are used for research purposes or support purposes, but, and this is I think the most important thing, when it's done properly, and it sounds like you're doing it properly, Troels, there is an exchange of information, and the benefit that the student gets is they're working on an actual system, and they're getting actual practical experience on what that's like. And that's something that often, if you don't go into these kind of things, you may think, oh, they're just using me. But if they're done right, what they're doing is giving you great experience working in these areas. And that's invaluable. I think the only other students that would get access to that kind of experience would be co-op students working in the industry, and then it becomes a question of what company you're working for, how well you're supported. But I just sort of point that out there, because a lot of times people think, oh, but they're just using me, to do this. But honestly, there is a real advantage. If you understand what your advantage could be, you can leverage that into great experience. And just by the questions, the thing when I went back to school to do my master's was, when I went back into that, I thought I'd spent 15, 20 years having to discover things in practical applications. And suddenly I could just ask a question, and somebody would say, well, that's a good question, and start to answer the question. It was just like, you mean I don't have to go out and figure out what's going on? You're going to give me a framework to work from? It's until you've been in the real world, you don't have a real sense of how rare and affirming that is, just have somebody saying, oh, well, these people are doing that kind of research. You probably want to look at that. Those signposts don't exist when you're dealing with things, you're exploring things. There's just no signposts out there.
Yeah, usually we would wait to do this maybe at the end, but it seems topical. If I recall, I saw a tweet from you, Troels, that was saying that you actually have open, was it PhD positions, I think?
Yes, I have an open PhD position. The application deadline is somewhere in mid-October, so I guess the listeners to this podcast will have time to apply.
Yeah. So yeah, I mean, I was in the back of my head, going to hang on to that to announce at the end. But seeing as we're talking about it right now, I guess, we'll put a link in the show notes for if you happen to be looking to do graduate work on compiler design. Could be something that definitely, especially if you're listening to this podcast, you might be interested in.
That's not free labor. You get paid for being a PhD student.
This is true. Yes.
But Bob, I think you're very right that the students do get something out of it. Now, when I recruit students for these projects, first of all, they're volunteers, and I make no secret about the fact that these are applied projects, and there is some overhead in trying to create production quality code. And so I try to be honest about it, and we're still developing our technique. So the last batch of projects I ran very much like I would like an open source contribution. So I had them open pull requests very early, gave them detailed code reviews all along, and that worked out pretty well. They were probably the most successful batch of projects we've had so far. But still, there is a significant amount of overhead that is in principle not necessary. You can get a top grade without writing production quality code, even for an applied project. But some students really like the experience of working on something real, and I expect that they also feel more accomplished afterwards because they've written something that's actually going to be used.
Yeah, there's a form of learning I think it's called experiential learning, where you put the student through the experience. I taught an online television course in production so that you run your own television studio. But what you do is you present the students with a series of problems that simulate what a person who's running a television studio would go through. And in that case, by the end of, I think it was a 7-week semester, at the end of the semester, they had a very, very deep understanding of what a person running a television facility would feel and understand, because they had seen the challenges and realized the trade-offs that you have to make all the time. And that's not something that usually is explored unless you're putting a person into the experience.
So yeah, I think, not to switch topics, but there was, at some point on the stack of things we were talking about, you had mentioned, and I can't recall if we actually got to the end of that question, was how you stumbled onto the array languages, because you sort of started with standard ML, then picked up, or Common Lisp before that, then picked up Haskell, which you said you've been doing most of your development in. And then you said along the way you kind of oddly stumbled into array languages.
Right. Okay. So that's actually also a bit somewhat interesting. The department where I'm at, DIKU, got a grant or created a large research project with a lot of money from the government around 2011 to investigate high-performance financial IT. The project, it was called Hyperfit. And it had a bunch of industrial collaborators. So one of them was SimCorp, which I think are the largest commercial users of APL. Another was Dialog, which you all know. So because a lot of these companies, especially SimCorp, had a bunch of financial code, a lot of it written in APL, and they wanted it to run faster. That was the idea. Financial companies, what SimCorp sells is a portfolio management system to people, places like pension funds and so on. And this system has to constantly compute the risk of the portfolio, how much it's worth based on potential market fluctuations and so on. A bunch of math that I never quite managed to understand, but it's very computationally heavy, and a lot of it is written in APL. So there was this idea that they wanted it to run faster because if you have a large portfolio, you need to be able to very rapidly determine how much it's worth. There are some legal requirements that I also didn't fully understand. So we had this APL angle. There was APL code out there, and we had this angle that we wanted performance, which implies parallel programming, and especially in those days, GPUs, and still GPUs for that matter. So this Hyperfit project investigated many things concurrently. One was investigating how you can analyze and transform APL. So one of my colleagues, Martin Elsman, developed an APL compiler called Tail, which did type inference of APL code and turned into a typed intermediate language. And we'll maybe return to that. Another investigated high-performance GPU programming, and he did it by kind of working backwards. He took a bunch of programs or algorithms, like maybe sequential C++ programs, and then he implemented them in GPU code, in CUDA or in OpenShell, and optimized them as well he could to make it run really fast. And then he looked at the generated code. And he reasoned, well, how could a compiler have generated this? Because the people who actually need these computations, actuaries or whoever, are not going to be writing hand-tuned GPU code. That's not within their purview. So we had this idea that they needed a high-level language, but we wanted to eventually generate very efficient GPU code. We worked backwards from the hand-tuned code and figure out, well, what kind of compiler optimization could have produced this code? And then what kind of language would have allowed those optimizations? And then we kind of work backwards, and eventually we reach an ML-like functional language with basic parallel constructs like map, scan, reduce, which is also the APL array programming vocabulary, essentially. So we kind of work backwards and reach something, the very core of APL, the static core, you can say, without the dynamic behavior. And then because another part of Hyperfit was working on actual real APL, they kind of converged and connected at some point. And that was how I got into both parallel programming and APL. And I kind of meandered into all of this because I was just interested in writing compilers. And there were a bunch of people there who needed compilers to be written.
Interesting. So to recap, because I want to make sure I didn't miss any of the connections there. In 2011, I think that was the year, a bunch of grant money showed up because of this, and a part of the people funding that was SimCorp and Dialog, who obviously had a vested interest in APL. At that point, was Futhark already existed, or
no, it didn't. So Futhark was a language that eventually rose out of this idea that we needed a language that could allow the transformations that would eventually turn into highly performant GPU code. But it was kind of the design bottom up, where we started by looking at the kind of code we wanted to generate. And originally, we didn't even want to create a language. We wanted to create a compiler, and then later on, we would figure out which language that compiler would then transform. And at some point, we thought it would be APL, and at some point it was actually APL.
Interesting.
But we really just wanted. So Futhark was originally supposed to be a core language, so an intermediate representation for a compiler, and it was always assumed that something else would be compiled to Futhark, and we just gave it a surface syntax only so we could write benchmark programs, so we could test our compiler. But then eventually it grew because language design is fun. But it wasn't really planned that way. And the language design part is, as I think I mentioned before, not really, or wasn't originally the academic work. That was just the hobby for me.
Interesting. So Futhark actually was initially designed or planned to be more of a intermediate language in between, accelerated, CUDA or GPU code, whatever that looks like, and then some higher level language, which, as you mentioned, even at one point was actually APL.
Yes.
Well, the obvious question here is, what's wrong with APL for our purposes?
Okay, so at that point, Codfns didn't exist, so nobody had compiled APL to GPU code, or maybe even highly efficient parallel code. I wasn't really that involved in the APL side of things.
There's one compiler to single assignment C, at least.
Yeah, Apex, but I think either it wasn't available at that time or it was. I don't remember.
I think it's available now.
Yeah, I think it has been. But so that is what Apple Tail did, right? Eventually, more or less.
Yes. So that compiled APL into a language called Tail, which is basically just explicitly typed APL. And it only supported a subset of APL, both because, it was one person doing it, and APL is a big language. And also there are probably some parts of APL, some of the very dynamic behavior that you cannot compile, probably. But there's a subset of well-behaved APL that isn't actually that difficult to analyze for a compiler. And that was, so he created this tail compiler, and he wrote a code generator that generated sequential C code. And I think they added some OpenMP for multi-core execution at some point.
Yeah.
But then we also had some students take this tail, which was compiled from APL, and turn that into Futhark. And that was when APL was really probably the most flexible surface interface to the Futhark compiler. And it actually ran quite fast, and we wrote a paper about it, showed that you could then compile APL code to GPU code and get significant speed up over handwritten C code. That was pretty fun work.
And so just so the listener is keeping up with us, because I've read a few of the Tail papers. Tail stands for Typed Array Intermediate Language, correct?
Yeah, that's right.
And so it sounds like Tail and Futhark were developed at the same time, or was there a...
Yeah, pretty much. So again, this Hyperfit project was large by academic standards. So you had lots of people working concurrently on things that perhaps try to solve the same problem, but there was no foundation. So there's a bunch of things growing up at the same time, right. And some of them eventually died out, and others kept living on. And some of them kind of joined forces later, like Tail and Futhark did. That's just how it is in academia. There were lots of other offshoots that also.
And so at a certain point in time, Tail was being used to transpile or compile APL code down into the Futhark intermediate language as it was at the time, because it was less of a language as it exists today and more of a sort of IR at the time.
Exactly. And this was before Futhark had things like polymorphism, which APL does have in some sense. So it was actually significantly more powerful than Futhark was.
Interesting. And so when you say polymorphism there, do you mean like type classes in Haskell, or do you mean like rank polymorphism?
I mean parametric polymorphism.
Parametric polymorphism, okay.
So even more basic than that.
Right. Interesting. And so then, so we're at the point now where APL is being compiled with Tail into Futhark, which is more of an IR instead of a language. And how did things progress from there to where they are kind of today?
Well, the Tail compiler doesn't work anymore, at least not the part that generates Futhark code, because Futhark changes was like 5 years ago. So Futhark has changed since then. The reason we didn't go further with that is that APL turned out to have some handling the full scope of APL turned out to be problematic. Like APL is a big language, and for this to be practically useful on real APL programs, you probably need to handle a significant subset of APL. And when we looked at the kind of industrial APL code that this might apply to, it wasn't then that code wasn't written in a style that was compatible with what Tail could handle. I mean, a lot of industrial APL code isn't really this kind of minimalist tacit style that most APL hobbyists or enthusiasts like, and that I also like. That's the stuff that fascinates me about APL. It's more like it's more imperative in style, and it uses a lot of what you would probably call legacy features. But I don't think industry agrees that they are legacy. So it just turned out to be a lot of effort to handle industrial APL code. And that was effort we couldn't justify putting in because we were compiler researchers. We didn't really want to be in the language front-end business. So it was easier for us to just extend the Futhark's surface language, the kind of intermediate representation, so we can continue with our compiler research, which was what we were really there to do.
Yeah, I think that's actually how a lot of compiler work at Dialog went as well. We and I didn't work on any compiled APL projects, but aside from Codfns, which is still in progress, I guess, like Dialog worked on a bytecode compiler, which you can run, but the basic conclusion there was that it's just too much work to get all this code that's out there and running and using whatever old features APL has that have been thrown in over the years. It's too much work to get that all to run on the compiler. And so what our response to that was to end up working on speeding up the interpreter and its handling of scalar code instead. But you can also, if you're not working at an APL vendor, go the route of changing your programming language, of course.
Interesting. I did not know that at one point Dialog Limited was working on a compiler, a bytecode compiler.
Yeah, that was about the first thing that Jay's big project when he started working at Dialog.
That's Foad, yeah, not the J programming language.
Endless source of confusion. But yeah, so he had a lot of compiler experience before that, and so he started working on a bytecode compiler there, which it shipped with Dialog. It works. You can run it. I think
it's 400 IBeam.
Yeah, and the usual numbers I hear are roughly 2 times faster for scalar code if it works well, but it's just too hard to maintain and all, I think is the...
One of the things you just mentioned was that maybe the tacit or maybe what a lot more hobbyists are interested in, that style of writing may be more conducive to parallel programming, at least the way Futhark does it. Is that something that maybe gives us hope that all this, trying to do the fancy little tricks and elegant code, and I think often what Stephen refers to as cool code, that kind of program. Often when I look at applications in industry, you're right. There's a whole lot of sequential working through cases, working through selects, those kind of things is very practical. And I'm not arguing against that because it's also actually pretty easy to figure out, which is I think why they do it. But when you actually can create something else, the same thing in a couple of lines that does it elegantly and uses the primitives, I suppose that's the reason that it's a little easier to compile to. Is that true?
Well, sort of. So tacit isn't an advantage for a compiler because that's just a question of notation. But what tacit style does is encourage a data flow that is based on bulk operations on data, and is kind of like I guess in APL we write to left, so a single pipeline of bulk transformations of data. This is what also Aaron Hsu's observation in his Codfns thesis, and that style of programming is very friendly to compilers and interpreters for that matter. That is just a very machine-friendly way of programming. And I think the big lesson of APL is really that it's also a very human-friendly way of programming. And APL nowadays probably isn't even the main example of that. I think Numpy is probably the main demonstration that massively parallel computing based on expressing bulk operations on data structures is both friendly to humans and to computers. That's Numpy is what I usually point to as my example when I teach this stuff. But APL, of course, did it before anyone else, and is still doing it in a more flexible way. So it's not about tacit as such. Well, I like tacit because of its elegance. But if I have to look at it pragmatically as what is helpful to a compiler, then it's not really the tacit style itself. You can give your variables names. That's fine. The compiler doesn't care. But it helps that you are encouraged to think in terms of data flow and bulk operations.
Yeah, the tacit part of it just becomes what moves you into thinking that way. You can introduce variables, and I suppose that's almost a hybrid, I would think, for somebody who's programming, because in some ways the explicit looks a little bit more obvious where you're bringing in variables, but the tacit actually enforces you to work that way because you don't have the variables to work with.
Yes. Well, I don't know if enough to say whether it forces you to do it, but it strongly encourages you to write in a way that has machine sympathy.
I like your way of phrasing it much better.
Yeah, there's something that's true in at least interpreted APL, I think, where it's the array-oriented way of doing it is focusing on the transformations and taking, applying as small a collection of primitives as you can get away with to as large a set of data, and then chaining those together. But I suppose when it's a compiler, since it can analyze that ahead of time, it can do the joining for you, whereas someone using the interpreter has to think of those steps sort of independently.
And yes, and there is actually also another significant difference here, because the compiler does allow you to deviate from this paradigm in ways that are also more machine friendly. So for example, my favorite example of this is computing the Mandelbrot set. So in the Mandelbrot set, you have a huge bunch of pixels, points in the complex plane. For each of those points, you need to do essentially a while loop and then count how many iterations you get through the while loop before you have your termination criterion is reached, and then you can turn the trip count of that loop into a pretty color. That's why people want to compute it. But that is very parallel, because all of the points can be computed independently. But that while loop in there is not very easy to express in an idiomatic way in APL, because in APL you want your sequential looping on top, and then you do bulk operations on entire arrays. But that's not really a very efficient way to express this, because the different points might need to do different number of iterations through the loop. So you really don't want some of them to exit early. Also, I think the idiomatic way to do this in APL is to continue looping across all of the points as long as at least one of them still needs to go through its small little loop. And that eventually involves repeatedly manifesting the entire big array of loops, that entire big array of intermediate states in memory, and then reading the back in all the time. And that's very, very expensive in terms of memory traffic. Now, the optimal way of doing it is just to have a single small sequential loop for each thread or each point or whatever, with the intermediate values kept in registers. But that's kind of a nested thing. You can write it in APL. I don't see why not, but I don't think an interpreter would be able to handle it, because it will essentially be an each containing a while loop over a big array. And I don't think. Yeah, but to a compiler, that's not a problem. It's just, okay, you have a parallel loop, okay, and I'll generate code for the loop inside, and then a bunch of threads. So that's something that a compiler can do that an interpreter cannot.
Yeah, it would be a lot slower. Although it is a little disappointing to me. So you can't run, well, I guess you could, but you don't want to run, say, 4 points at a time and stop when all of those are finished.
Well, I mean, you can do that, but I wouldn't want the human to write the code like that. I mean, that's...
Yeah, it's definitely, that's something that you'd have to be actively machine sympathetic instead of sort of just using the language.
Yeah, and maybe a compiler can even generate that for you.
Huh, yeah.
That's not particularly difficult. That's essentially how a GPU would execute the code anyway. It would just implicitly do it, well, I guess 16 at a time instead of 4 at a time.
So I have a queue of questions that we're going to hop around, and maybe we'll splice in other folks' questions. So that hopefully we can get to all before the end. So one of them, I think it was kind of answered at one point. But the question is that, sort of on the Futhark website, it has a description of the Futhark language and, a few of the keywords. In the middle are, a purely functional array language.
Yes.
And so I guess and we talked about this a tiny bit at the end of the last episode, is what about Futhark sort of gives it that array? Because it definitely looks different. And you mentioned earlier that as you were working backwards from the sort of compiled, accelerated code, you got back to this sort of core set of primitives, map, scans, reduces, and that maybe that is part of the answer anyway. So I'll let you answer, where the array part comes in, because it's both functional like Haskell, and then also array insert your answer.
Yeah, so you spent the last episode discussing what an array language is. And I'm an academic, so I'm a big fan of discussing definitions. And to me, array language is a social definition. So my definition would be that it's an array language if you get to talk about it on ArrayCast.
Well, he's got us there.
So in that sense, Futhark is now an array language, but it wasn't previously. But so I'm actually, if you look at the various things we've written about Futhark over the years, you'll see we're not even consistent in what we call it. Originally, we just called it an array language. Nowadays, I tend to call it a functional array language, which is a term that Sven Schultz, the creator of SAC, came up with. And I'm mostly using it because Futhark isn't really an array language in the sense that APL is. It lacks a lot of the features that you mentioned as important. It doesn't have a rank polymorphism. That's probably the most important omission.
Mm-hmm. Yeah, you do have to write your maps.
Yeah, you have to write a lot of maps. We actually have an idea of how to eliminate some of those.
Yeah, so you think it won't be that way forever, is your thinking?
Right. So Futhark is a typed language, and that's kind of because I was trained to like typed languages, but also partly because it really helps a compiler when it doesn't have to work hard to figure out what things are. And rank polymorphism, you can do it in a type system, but it's really complicated. There have been entire PhD theses written about how to incorporate APL-style rank polymorphism in a type system, and it tends to conflict a lot with other type system features that you might want to have, like parametric polymorphism. I actually have a suspicion that it's not possible to combine rank polymorphism with parametric polymorphism at all. It's simply fundamentally incompatible. But I haven't yet proven it. That's a paper I want to get around to writing. So in Futhark, nobody likes writing map all the time. I mean, it's nice if you can, just to make it clear what's going on, but when you write very heavy matrix-oriented numerical code in Futhark, it really sucks having to write map all the time. So we have this idea, we have this hypothesis that a lot of rank polymorphism, at least in non-APL code, is pretty simple and really just corresponds to inserting a bunch of maps on top, which is also exactly what the leading array axis theory is basically doing.
Pretty much.
Yeah, so we think that you can actually pretty easily in a standard ML types checker do some kind of map inference where when we apply a function, you just check, okay, this function call isn't well typed, but if we added a bunch of maps on top, would it be well typed? And then we can just do that. So this would be less flexible than APL-style rank polymorphism. In particular, you would not be able to write rank polymorphic functions, but your function applications would then be rank polymorphic in a limited sense. And that means the type system doesn't get more complicated. In contrast, SAC, single assignment C, does have rank polymorphism, and you can directly write a rank polymorphic function, and you can do all kinds of cool things where you can do rank specializations and so on.
Right.
But it really complicates the type system, and they don't have parametric polymorphism. And I think for the reason that it doesn't really work with rank polymorphism.
One of the things that occurs to me that seems to be cropping up as a pattern is that you seem to work backwards to what you want to get to. But honestly, you laugh, but I think that's really neat. And often when you're trying to approach problems, it's that kind of change in perspective that will open up a problem for you rather than everybody else tries to do the other way and they just keep hitting this brick wall. Well, by going backwards, you actually find a way around the brick wall to getting your solution.
It at least allows you to think differently. So, I mean, there are lots of really nice programming languages out there. I mean, I like Haskell a lot, and I also like APL. I actually like K a little more, but that's a different thing. But a lot of these languages were written with humans in mind, and then later on we try to figure out how to make them run efficiently in computers. And sometimes you get lucky. I mean, when Ken Iverson designed APL, he was pretty much thinking about humans, and it just turned out to also have a lot of mechanical sympathy. It was pretty easy to make APL run surprisingly fast. But a lot of languages weren't really designed with that in mind. So if we wanted a niche, if we wanted to have a language that we could compile efficiently, we figured that we would have to start from the other direction and start by looking at the code we wanted to generate.
So I've realized that we've mentioned now parametric polymorphism maybe 2 or 3 times, and there's probably a handful of listeners that aren't familiar with that term. So I'll do my best to define it, and then Troels can correct me. So rank polymorphism, we've talked about a ton. It's basically implicit iteration where you don't need to map. So scalars work with matrices, etc. Parametric, from my understanding, is when you have a function that works the same way for multiple different types. And then in Haskell, they have both parametric and ad hoc polymorphism. Ad hoc is where you have same named functions that have different behavior for different types. So you use type classes in order to get that. And famously, Go has not had parametric polymorphism for a very long time. I think in 1.18, they added it for the Go language. But what that meant is that, and this is like my favorite example to kind of give Go a hard time, is that when you want to take the maximum of 2 integers, you can't do that. They have a max function, but it only works on floats. So in Go, you have to cast your integers into floats, then pass those 2 numbers to your maximum function, and then you get a float back, and then you cast that back into an integer, which if you are in a language with row type polymorphism like Python or generic programming in C++, like that seems incredibly backwards that you can't support. You have to write a function n different times for the n different types you have in order to get it to work. And so, yeah, Troels, did I get that close enough, or is there's things you want to add to that?
Yes, but I think the really crucial part you didn't spend a lot of words on. So parametric polymorphism is about writing functions that do the same thing for different types. That's really that's more difficult than it sounds, because for example, when you have the identity function that has type x to x for any x, and just by that type you can deduce that it must be either the identity function or a function that explodes, that diverges, doesn't return anything. And that really breaks down very easily if you allow code to inspect the actual type. Like if you have reflection, for example, that's the most obvious way. Then you break what's called parametricity. That means that you can, and that means you have risks that the code that is supposed to be reusable isn't as reusable as you expected, because it doesn't anymore do the same thing for the same types. And it no longer does the same thing for different types. And the problem when you add rank polymorphism is that you lose parametricity, because you can expect things based on that shape. If you take any A, and you ask for its shape, then you get back a value that depends on the actual type. Because if it's a matrix, you get back a 2-element vector. If it's a vector, you get back 1-element vector. So you lose parametricity when you add rank polymorphism. And I don't see a way to fix that without either significantly restricting rank polymorphism, and then you might not even want to have it anymore, or losing parametricity, which is kind of the main advantage of parametric polymorphism. Or maybe I'm just too fundamentalist.
You would sort of need if you were to try and extend that parametric view of it, you'd need a different type for each shape of array. Is that right?
Yes, exactly. And that's how it is when you write.
It's impractical, but
that's how you do it when you write in Futhark, for example. So, and the hypothesis we then have is that most instances of array polymorphism really are just about adding more implicit maps at the application side. And if you do that, then you haven't touched the type system and you can get away with it. But there are some functions that you cannot write this way. But I also have a suspicion that in APL, rank polymorphism is really important, because it's about doing entire flat bulk operations on data, and then the next operation, and so on in a pipeline. Nested operations in APL are kind of discouraged because interpreters don't handle them well, because then you have these complicated code inside of your defs, and the interpreter will have to scalarize the outer part or something like that. I don't remember what it's called.
Well, the interpreter just spends more time running, because it has to run every time a primitive is applied. I think that's why rank polymorphism is really crucial in APL, because not only will it otherwise the code be larger, but it'll also run a lot slower. But in Futhark, you can say map with a complicated function, and that'll just work. There's no performance overhead. So a lot of Futhark code is more nested than would be good style in APL. And I think that's one reason why we can get away with not having rank polymorphism, only having a very limited form of rank polymorphism. So it would be interesting to ask someone like Sven Schultz from Single Assignment C, why they have rank polymorphism, because they also have a heavily optimizing compiler. So they don't have this performance requirement. So it may be that they have some insights I don't about why rank polymorphism is not just nice to have, but really important, even in the presence of an optimizing compiler.
But as you mentioned, they don't have parametric polymorphism, and that's I've mentioned my sort of array language comparison GitHub repository, and there's a table on that where I show reduce, scan, and outer product and how they exist in sort of 9 or 10 different array languages, and Single Assignment C is the only one that doesn't have any 3 of them, because Single Assignment C doesn't have support for basically generic operations. And when I talked to Bob Bernanke at the Toronto APL meetup a couple weeks ago, and he said that basically when he's working on Apex, his compiler that compiles APL down into single assignment C, he just has a bunch of macros, which is a very common thing you'll see in C code bases. So it's very interesting to sort of contrast these, Futhark sort of Haskell-inspired single assignment C inspired, and one has rank polymorphism but not parametric polymorphism, and the other one has parametric polymorphism but not rank polymorphism, and the trade-offs. Which kind of maybe takes me to one of the other questions that I had is, we haven't talked at all about SOACs, or second-order array combinators.
Yes.
Which basically, if you go to one of the prelude libraries in the Futhark documentation, it talks about map scans and reductions, and even has, I think Futhark's one of the only languages that I know of that has both a reduce and then a reduce underscore commutative, or COMM, which has basically two different reductions that have different requirements on like the associativity and commutativity, which is something we've talked about in NVIDIA parallel libraries, of the fact that we are missing a couple of these. Do you want to talk a little bit about how do you pronounce them? Is it SOACs or SOACs? And
we just say SOACs is probably what you should say. So yeah, those are interesting, and those are, so these are things like map and reduce and scan, as you said, and these are pretty much all taken from pretty much original APL. Because original APL did come with essentially the core of a very effective vocabulary for parallel programming. Now, APL unfortunately got some things a bit wrong because it assigns sequential semantics to them. So the APL reduce is more like a fold, in that it's guaranteed to be left to right execution, which means you can parallelize it because you can pass in. You have no idea what kind of function is passed in. And APL's...
Well, what you do is inspect at runtime.
Yeah, you can check it. Yes, sure. And the scan in APL is...
It's so bad. It's so bad. BQN fixed it. BQN fixed it.
Yes. I think all successor APLs fixed it.
Not really, Jay.
Yeah, but it's unfortunate because that was really the core of it. And what we realized pretty early on is that you don't really need much more than that. And even things like scan and reduce, they don't really have to be primitives. It's useful to have them as a primitive so the compiler can knows what they are and can generate custom code for them because they are so common. But they're not. Technically, you don't actually need them. They're more for humans than for machines. So they are second order in the sense that you pass in the function that you want to use. So for map, you give it the function as an argument. For reduce, you give it an operator. For scan, you give it an operator. And to enable parallel execution, some algebraic properties must hold for these operators. Associativity is the main one for reduction, and there must also be a neutral element. And this has, in most cases, most reductions are with plus or multiply or max or something that is known to be associative and commutative. There are a few cases where it's useful to be able to pass in a custom operator, but it has been our experience that humans are really bad at thinking about associativity. So it's very common for people to write operators that are not actually associative, and then they get the wrong results because then the parallelization doesn't work out. And that's so. Some of my colleagues would say that it's a mistake to even allow user-provided operators because it's so easy to get them wrong, and it's kind of it's a big hole in the language. You can say you can get non-deterministic results, but on the other hand, sometimes it's just so convenient, and it can really help performance. You can do something very complicated in just one reduce that would otherwise take multiple scans or whatnot.
And so, do these in general, like the special thing about them is that when provided the correct operators with the correct requirements, it'll be highly accelerated, or is there something more in terms of like if you chain them together in a certain way that they'll fuse? Because I think it says, what does it say at the top of the page, that they can be exploited by the compiler. Like, does exploitation just mean like simple things or fancy things? It
means fancy things. So the compiler knows what a scan is, and it knows what a reduce is. These are primitives in the intermediate language, and there's a few of those. And it has a fusion engine that knows of how these things can be combined, so you can reduce multiple passes into one pass. There is we have a flattening algorithm that determines when you nest these things how they should be flattened out so they can fit on non-nested hardware like GPUs. So everything is ultimately expressed in terms of, I think we have 5 primitives at the very bottom level, and the compiler knows about those. And adding new primitives is something we try to do very rarely, because when you add a new primitive, you need to worry about how it interacts with everything else. I mean, you have combinatorial problem here. It's not like an interpreter where if you add a new thing, you just have to make that thing run fast in isolation. We also have to consider its interaction with everything else. So we try to keep the number very, very low.
Well, I got to hold this over the K people. I'll say, oh, your language has 25 primitives. Well, the Futhark intermediate language has 5.
Oh, that's the parallel primitives. You also count the scalar ones. We have tons. I mean, we have nine built-in types, and each of those has a full arithmetic library. I guess there's hundreds if you count all of them.
I realize now why I think you have 5 maps. Is it because you don't have rank polymorphism?
Oh, you mean we have... actually, that's different.
Or do they do very different things?
No, so you mean we have map 1, map 2, map 3, map 4, and map 5.
Yeah, that I mean, I didn't look in detail. I saw that.
No,
and
that's
weird.
not rank polymorphism. That's map 1 is when you want to have a function that takes 1 argument over 1 array. Map 2 is when you want to have a function that takes 2 arguments over 2 arrays. So it's just shorthand for first zipping and then mapping. Because it's
a notational deficit, not a...
And this is actually something that exists in like many functional languages. I think Haskell, Scala, they all like, I think they have map, they have zip width, and then they have like zip width 3, 4, 5, 6, which is...
Yeah, it's exactly that.
Well, and APL's got this problem pretty badly because it has each is map and zip width, so it goes 1 and 2, and you can't go past that. So actually, K does do a good job of that. You can map over a large number of arrays, but APL does not.
A kitten that has entered Troels' well, the kitten's been visiting throughout the episode.
Yeah, I'm not sure I did feed him. I'm not sure why he's...
he wants a mention on the podcast. He knows he hasn't been... Or is it a he or she?
It's a he. His name is Toxoplasma gondii.
What?
I asked the same question when we did the tech check. Explain the background to that, to Troels.
Yeah, so the Toxoplasma gondii is a parasite that lives inside of cats and is reputed to cause crazy cat lady syndrome in humans.
Oh yeah, is this the thing that you're not supposed to have if you're pregnant?
Yes, it's mostly not. I mean, I don't think it's dangerous beyond that. It affects I think rodents. It makes them more risk-seeking, so then they get eaten by cats, and then that's the life cycle of the parasite.
You named your cat after that.
We should wrap up, I guess, maybe the last section, which had a visit from a kitten, is to say that it sounds like if you're writing Futhark code, if you can express a majority of your program, or at least the computation significant hotspot of it in these SOAC combinators, you're going to get a huge performance windfall because of this fusion algebra that you mentioned.
Yeah, but it's not just because of that. It's also because if you just write Futhark, you can write a sequential loop, and that's just sequential. It's not a parallelizing compiler. It doesn't analyze your code to figure out whether it can parallelize something that you wrote as sequential. Mm-hmm. You have to use the parallel vocabulary to get performance. And there's actually a wonderful thing called a parallel cost model that tells you asymptotically whether something will parallel or not. So even without worrying about how the code will look like on a GPU or on a multi-core or whatever, you can reason about, well, what is the maximum number of sequential dependencies I have in my program? So how can I expect it to scale in runtime when the data set changes? There was some wonderful work done by, I think Guy Blalock mostly in the early 90s about parallel cost models as a high-level concept. I think you could also write a parallel cost model for APL. It's a very, very general technique. So that's how I would like programmers to think about Futhark code that they write. Not about this fusion stuff. Fusion is just a constant time optimization. It's great when it works, and it matters, of course, but it's not what gives you the parallelism. It just means you have a little bit less memory traffic, or a lot less memory traffic.
Interesting.
And Futhark is in many ways kind of a low-level language in that it doesn't have rank polymorphism. It doesn't have type classes. It's sometimes a bit tedious to write, but it does encourage you to think at a very high level about what your parallelism looks like. And I think that's very useful to any programmer, also programmers in array languages. And then, of course, in array languages, most programmers do this already because it's a natural way to phrase things.
Yeah, we'll put a link to Guy Blalock's. He's got a bunch of great papers, but he also has a website that hosts most of his Nestle work, which I'm sure, Troels, you're familiar with, which is his sort of toy ML accelerated language, where he has a bunch of implementations of algorithms like scans and stuff, which is pretty it's pretty interesting to read through and very illustrative of the ideas there. I think we should end with the question, why do you like K better? But before we do that, are there any other questions? I feel like we're going to have you back at some point because I feel like we've only touched the surface. And there's maybe what we'll try and do is we'll try and cycle through. We'll try and get someone from Dex on, try and get someone from Single Assignment C on, and we can go through all the array, parallel languages. Bring Aaron back on to talk about Codfns.
By the way, the term that I use for these is typed array languages because they all share that static typing.
Yeah, that's not a bad term.
Typed array languages. So what fit all? So Futhark, Single Assignment C.
So everything you just mentioned: Futhark, Dex, Single Assignment C.
Does Codfns count?
No, because it's dynamically typed.
I mean, it compiles down to arrayfire, right? So which is typed. But that's the tricky thing about this, right?
Yeah. So the target is statically typed, but the language is dynamically typed. I think it moves all the type checks to runtime.
What about Remora?
Yeah, Remora, I assume when you mentioned there's been PhD dissertations written about typed languages with rank polymorphism, you were referring to Remora, and that was Justin Slepek's dissertation. Yeah. Is Remora?
I think it's typed.
Well, it is typed. But it's essentially APL with types. So why isn't it just an array language?
Well, because a central feature of APLs is that it's dynamically typed, I would say.
We're back into that discussion.
We're back into the last episode of...
I mean, I'm not saying typed array languages. I consider typed array to be a subcategory of array languages. So it is also an array language.
Interesting. So now we need to whip out my now what upgraded from a paint picture to a PowerPoint Venn diagram, and I got to put a type circle in it now.
It's not very Iversonian to care what a decimal point does to the computer. Yeah, I guess, because he was on a whiteboard, just like number's a number.
And so now we fire up the YouTube and the Venn diagrams, and everybody who's walking their dogs is ripping their hair out. Although I did get feedback that people said it wasn't too hard to follow, so that was encouraging.
Yeah, and it's got. I'm surprised. I thought it would only get a couple hundred views. What we're talking about, Troels, is at the tail end of our last episode, I launched a Paint application and started drawing a Venn diagram, and we posted it to YouTube, and I think it's gotten close to 3,000 or 4,000 views now, which. I'm not sure how many people actually started watching it and signed up for the whole thing and stayed through it, but. All right, so we'll have you back in the future. But before we let you go, even though we're a little bit over the hour marks, we appreciate you staying with us. You mentioned at some point, and we can't not revisit this question, that you prefer K to APL. So the floor is yours, Troels. Tell us why.
Okay, so this is going to be a very boring answer. So the main reason is that my kind of first love in programming languages was Common Lisp, and K is more like Lisp than the other APL dialects.
Interesting. Do you stay up to date with all the different Ks? And Shakti and stuff like that, or
no, not really. But when I do program in K, I think it's called Kona. I'm not a very advanced K programmer. I just pick one of the free implementations, and they all support what I need, which is just for playing around.
Is Kona? Which K is that? Is that K6?
No, I think it's 3 or 4.
Okay.
So like KXK.
Mm-hmm.
And being a Lisp fan, what about April? Have you followed that at all?
A little. I really enjoyed the podcast you did about that, and I did. So there was APL in Lisp. That's great. But one of the things he said really I realized was a phrasing of a thought that I've had for a while, which is that APL is really great for the expressions, but it's less great at the control flow that centers around it. And in dialogue APL, you have the APL, and it's great. But the imperative things are not really very nice. I mean, you can do the imperative control flow in dialogue APL, but it's not great. Whereas if you had Common Lisp around surrounding it instead, that's really good at imperative control flow and has a great object system and all of that nice stuff. Then maybe that's really what APL should be. It's the language for the expressions, for the computation, but not for the tedious bookkeeping on top. I haven't actually tried April, but it's close to what I think may actually be a good design for a language or a programming environment or whatever you want to call it.
I think Andrew Seng will be very happy to hear you say that. I'll probably get an email about that, and we'll put a link in back to that episode because it was interesting, and he is using a combination of Lisp and APL and using Lisp for a lot of the imperative stuff that allows more flexibility in controlling the structure of your program.
Yeah, do we enumerate the list when we had Andrew on? Because there was basically APL in Common Lisp, aka April, APL in Python, aka Pineapple, APL in Julia, which I don't actually think has a name, but someone as a lightning talk once implemented some subset of APL.
Yeah, there's an APL.jl is I think just what you call it.
And so it's interesting. I'm not sure if there's more of,
There's May as well, which is the other Lisp.
Oh, Closure?
That's right, Closure.
Yeah. Right, because May comes after April. So there's what, 4 different implementations of APL in insert language.
Well, Pineapple is more of a bridge.
Or a bridge.
Yeah.
It's not an implementation.
So we're at
but
3.
It is kind of interesting to think that potentially like the evolution of APL is more like regex, where you end up with like little regex expressions.
No. I think you're thinking too narrowly. It's more like the like mathematical notation. Every programming language supports mathematical notation in its expressions. That is also just a sub-language. Like you can say plus, divide. APL is just like that.
Interesting. So you're thinking like, take the Julia language where you can define your own Unicode operators and add, the min and max glyphs as extensions to the infix operators of like plus, minus, and multiplies and kind of thing.
You have to think bigger.
Think bigger.
So
not thinking big enough.
We once interviewed Bjarne Storstrup, the C++ creator, what C++ would look like in 10,000 years. And he said that maybe by then it would have a decent syntax. And I think maybe what he meant is that the expression syntax would just be APL by that point.
Honestly, I think that's the thing when you talk about shoehorning APL concepts into other languages, you miss the simplicity of like being able to explore with the syntax, being able to just like chuck things together.
Yeah, that's true, but you could have kind of a prompt way to do that. I don't know. Programming language design is difficult.
Yeah.
We're saying it's like awkward to have to like write a string representation of an APL program and then have the piece of the sort of interface. Yeah,
you right. You don't want that. You need some kind of textual flexibility in the host language, so it's not just a string that that you execute. I don't know what it would look like. I think Common Lisp has a lot of flexibility, maybe, but
April still does that, I think.
Yeah, I think so.
It is an interesting thought experiment because, like, you think about, for all of us that work in Linux or, the shell in some other environment, and, how often are we catting the contents of some file and then piping it to, grep and then piping it to WC-L, all of which is, like, in my opinion, just as esoteric as the Unicode symbols in APL. But, like, that's like a bread and butter tool if you live in shell. And it's like, we all know that WC is word count and -L is lines, and like grepping to search for stuff and we learn this language that is to some extent foreign and like looks odd. It's like, what is cat and what is grep and what is WC? But because it's right there, people learn it as this like bread and butter tool. And it's interesting. Yeah, it's an interesting thought experiment to think about what would a future programming language that has some translated version, if Bjarne is saying in 10,000 years, will actually have a nice syntax. It's like, folks that use that all the time, it becomes just like second nature. It's like we could have some kind of merged, I don't know, Python or C++ language with all of the power of, the rank polymorphic glyphs of APL. And yeah, it would be neat. I would enjoy my day job much more if that was something like that exists for sure. Hopefully it doesn't take 10,000 years though, because unless cryogenic freezing happens and I've got the money for that, which I probably won't. I won't be around for that. So, all right, I think that's probably a good enough place to end it, seeing as we've gone over by quite a few minutes here. But thank you so much, Troels, for coming on and talking to us about Futhark and everything you know about sort of parallel computation. This has been so awesome. I've learned a ton, and I have to go now and find some papers to read about both Futhark and SAC to dig in a little bit deeper to this stuff, because it's super interesting to me, and I'm sure our listeners will enjoy the conversation thoroughly.
Well, let's hope so. And really, you should get one of the SAC guys on here. The SAC did everything before anyone else in terms of high performance, high level, functional-ish array programming.
Yeah, are you familiar with the folks? I know Ardom. I don't know Bodo Schulz. Like, who would be the best person, do you think, to reach out to have to talk about a single assignment C?
Sven Bodo is an extremely entertaining speaker. Artems is, I actually not seen Artems present. I know of him, but I would recommend Sven Bodo. I think he was also the original designer.
Okay, yeah. Well, we'll reach out and try and get. And he's been working on that since, was it the late 90s or early 2000s? So
Early 90s.
Yeah, early 90s. All right. So
I mean, before people thought this was a cool subject to work on.
Wow. Yeah, we'll throw a link as a teaser. There is I think it's a Microsoft. I was going to say Google Tech Talk, but I don't think it was actually Google. It was like a Microsoft research from 2006 or 7. He went and gave a talk on single assignment C, which is 15 years old at this point, but will be a little bit of a teaser for folks that are interested in learning more about languages in this space. And we'll try and get him on in a future episode. But once again, thank you so much for taking the time. This has been absolutely awesome. And with that, we will say, oh, wait, Bob's got one more thing to say.
I'm just going to plug, you can contact us at contact@arraycast.com. Because we've had some very interesting, we've always had really great interaction with the listeners, but I think in the last 2 weeks we had Scott Laughlin and then Stephen Apter actually chimed in again. Some really, really interesting things for us to think about, I think, for our next episode, which is a teaser. I think we're going to talk or may talk about Iversonian versus other array languages, but that can all change because we're very flexible, creative people, and who knows what we'll do next. And so maybe you just have to turn to the next episode. Sorry for interrupting what will be the wrap-up of the show.
Not a problem, not a problem. Contact@arraycast.com. All the links for all of the research and projects and papers we mentioned will be in the show notes. With that, we will say happy array programming.
Happy array programming.
And the kitten joined for the goodbye.